Welcome, everyone. It's a pleasure to introduce today's CBL alumnus, Jean-Pascal Pfister. I mean, I think all of you are kind of too young CBLers to have been here when Jean-Pascal was still among us in CBL. So Jean-Pascal did his PhD. Actually, he has a background in physics, and that he then did his PhD in computation and neuroscience in Wolfram Gerstner's lab at EPF, one of the best labs in Europe for that. And then he actually did a short stint in industry before I was fortunate enough at the time to attract him as a postdoc to my group, where he stayed for a couple of years. It was great fun and very successful, I should say. And Jean-Pascal, during his PhD already, has done some really interesting work on models of what is known in computation and neuroscience more broadly, of spike timing dependent plasticity. So a particular kind of biological way in which neural networks in the brain reconfigure their synaptic strengths depending on the timing of the precise timing of the activity of neurons in a network. So Jean-Pascal has done some really groundbreaking work in kind of mathematically analyzing how this actually happens during his PhD. And then during his postdoc with me, he has looked at other forms of so-called synaptic plasticity, whereby neurons change the strength of the synapses between them, but kind of more transiently. And he's shown a beautiful mathematical relationship between this particular form of biological synaptic plasticity and something that is going to be quite closely related to today's topic, Bayesian filtering. So he has done some really beautiful mathematical analytical work to show that the equations that are kind of commonly used to characterize this form of biological synaptic plasticity called short-term plasticity are actually at least under some conditions beautifully overlap with the equations that one would get for a particular Bayesian filtering problem that we thought at the time might be relevant for neurons to solve. And then he went on and established his own research group very successfully on a very prestigious Swiss grant, the SNF professorship grant, actually two different grants, an Ambizione grant and then a professorship grant at ETH Zurich, which is obviously one of the best universities in the world. And then from there, he moved on to Bern, to the University of Bern, another excellent Swiss university. And he has been doing a lot of interesting work, among which he continued working on Bayesian filtering and its relations to neuroscience in many different guises. So I think today he will tell us some more about that line of work, which really kind of beautifully combines kind of foundational work in control theory, statistical inference, and neuroscience, in particular computational neuroscience. So please, Jean-Pascal.
Thanks, Mate, for this very kind introduction. So can you hear me? Can
yes,
you hear me well?
I can.
Okay. I will try to share my screen. Here we go. Share. Okay. Okay. Can you see my screen correctly?
Yes.
Yes.
I believe so.
Okay.
I see your title slide.
Okay, that sounds good. Okay, so thanks again, Mate, for this very kind introduction. I have to say it's really nice to be back at CBL. Even though it's still a bit curious to be, back at CBL and the only one physically in CBL, but I really enjoyed all the group meetings during the sabbatical that I'm doing here, like during the last months, and the one-to-one individual discussions. So that has been really great so far. And I have to say, CBL was a very special time on my scientific journey. As Mate said, I was interested in synaptic plasticity and dynamical systems with Wolfram, and then coming to CBL, I really got exposed to this, Bayesian worldview, and this had a massive impact on, let's say, my research agenda. And I'll say I'm very thankful for the whole CBL atmosphere and, the environment that Mate also provided. That was just kind of the dream postdoc, at least from my perspective. So before starting, I really want to thank my lab members that have been absolutely brilliant in working on this topic between nonlinear filtering, which I'll define in a moment, and neuroscience. And it's especially Simone Soace, that has been doing his PhD and postdoc with me, has been really instrumental in this agenda. And Yannis Yegminat, I will present his work as well, apart from Ehsan Abedi as well, and also Anna Kuchiaite, which had also some really nice contributions. Yes, so the brain is faced with uncertainty at all possible levels. It's faced with ambiguity and uncertainty at all possible levels. Ion channels are very noisy. They stochastically open and close. Synapse are also stochastic transmission units with significant transmission failures. Neuron are stochastic spiking generation unit. The conversion from analog to digital is also very stochastic. Neural network are stochastic. And even at the behavioral level or the perceptual level, the brain is faced with a lot of ambiguities. So the question is, how can the brain face such uncertain environments, and even more being built with unreliable elements, and yet perform robust computation? And this has been a driving question for me for a long time. And I think this calls for a generic principle that enables the extraction of relevant information from noisy or ambiguous stimuli. And there's a mathematical framework that can deal with this, which is called nonlinear filtering. So essentially, my presentation will be divided in two main parts. So the first one will be a bit on theory, and the second part on the applications in neuroscience. So really, I should have mentioned it before, but please do interrupt me. I really enjoy questions. I think this is what makes science lively, is to have questions. So please do interrupt me if you have any questions. So I couldn't resist the temptation of illustrating what nonlinear filtering is with this historical moment that we all lived, and especially we as Swiss people lived on Monday. As you know, there's the Euro, and there was the 8th final, and this little team of Switzerland had to play against the world champion. And if you're goalkeeper and if you want to have a chance against one of the biggest football player, there's one thing that you have to do well, is to be able to track the position of the ball when the opponent is shooting the ball. So in an informal way, I would define nonlinear filtering as optimally extracting relevant information from dynamical and noisy observation. And this is why I really like nonlinear filtering, because it contains those two ingredients of time and noise, which are kind of my two favorite ingredients. And to some degree, I could say, I learned the time aspect with Wolfram, and maybe the noise aspect with Mate and the whole CBL team. Now, why is nonlinear Bayesian filtering relevant? I think there are two main reasons. One is, on the computational principle, it can be, we can frame perception as an act of nonlinear filtering, right? But it can also be applied to the neural network level, at the synapse level, at many different levels. And I think this is what makes nonlinear filtering relevant. But actually, nonlinear filtering could also be used as data analysis method in neuroscience, right? So if you think about decoding tasks, let's say you record some spikes from a rat in an environment and you want to estimate its position based on place sets. So this is the filtering problem. Or if you're faced with a control problem or neuroprosthetics device, you have to estimate the intention of the patient. Or if you do want to do, say, optimal experimental design, you're also starting to have some results in that direction. You also want to use nonlinear filtering. So I think it's really kind of a toolbox you want to have in your suitcase. Okay, so how do we define a nonlinear filtering problem? So in order to define it, you need to have a latent variable, let's say, which I will call x, which has some dynamics, like a deterministic dynamics, f of x, and a noisy contribution or a stochastic contribution. So here in my little example, x would define the position of the ball, and f would represent the physics, the laws of physics, so Newton's law, and maybe some noise, maybe there's some gust of wind, or there's some perturbation to the deterministic equations. Right, and if you want to estimate this, your latent variable, you can rely on some observations. And here, for example, for Jan Sommer, for the goalkeeper, he has some visual observation, which is a function of the latent state. It's a nonlinear function of the, let's say, the position of the ball, plus some noisy parts, which is also here described by a Wiener process. So W and V are Wiener processes. And here, so altogether, this defines a generative model. And so in the talk, there will be many times generative models, and they will always be like with this green box around. And the question here is the following. So based on past observations, let's say the observation y from 0 to t, what is my distribution, my so-called filtering distribution over x, over my latent variable, let's say given my past observations? Right, so in the first stage, we will assume that f, g, and sigma x and sigma y are known, but this assumption can be relaxed and learning can be kind of an addition layer that can be on top of it. Right, so how do we solve this problem? Actually, if you read the literature and go back to this mathematical literature from Kushner and Stratonovich in the 60s, actually, they already solved this problem for us. And so they have a fully analytical and exact solution for the filtering problem. So if P is your filtering, it's your filtering distribution, if you have xt given y from 0 to t, it follows some dynamics or some stochastic partial differential equation. Right? So the increment in P obeys some Fokker-Planck operator. Right? So we're interested, so if there's a distribution to a given time, we're interested in how much this distribution will change in a very small time increment, dt. So it has a deterministic part, which comes from the prior. So there's a prior dynamics, right? And this dp equal L dagger p dt is the so-called Fokker-Planck equation. So I just wrote here the Fokker-Planck operator in 1D to make it simple, but it depends on derivative of fp and the second derivative of sigma xp. Right, where f and sigma x defined the hidden dynamics, so the latent process, right? But now there's this additional term, g minus expectation of g, where the expectation are according to this distribution p, times dy minus expectation of g dt times p, right? So if the observations are very noisy, so this is the covariance matrix, the observation covariance matrix for the observation process. If this is really large, then this whole term goes to 0, and P will evolve only according to the prime, right? And if the noise is very small, then the observation term will dominate. So this looks really, I would say, fantastic to have the full-blown, complete solution. You can actually rewrite this equation in a weaker form, where you multiply by phi and integrate. So you, instead of looking how your filtering distribution evolves as a function of time, you look at how some function, nonlinear function, or how your moments of your distribution evolve, right? So 5x could be x, and then you look at how the mean evolves as a function of time. And you have the full solution here as well. You just have to transpose your operator, but essentially it has the same structure with a prior term and an observation term, right? So here Bayesian inference is really an addition of a prior plus a likelihood term, if you want. Right, so this looks fantastic. However, this equation cannot be used generically as such, right? So let's say if your function g is linear and phi is linear, this will lead you to second order term. So the evolution of the first moment will depend on the second moment, and then the evolution of second will depend on the third, etc. So you have a closure problem. So typically you need infinitely many moments. And this is not a surprise because P is already an infinite dimension object, even if X lives in one dimension. So yes, so the problem is non-closed except in very specific situation where, let's say for the Kalman filter, where all functions are linear. Okay, so because we cannot use as such this Kushner-Stratonovich equation, you have to rely on some form of approximation. So I just classified the existing nonlinear filters. So for example, the Kalman filter, it's a parametric filter. It is exact, but it works only in linear case. You have also approximate filter, like the extended Kalman filter, or the assumed density filter, or the variation filter. Yes, right. Or exact filter, I mean, in the sense that when the number of sample goes to infinity, they're exact. So those are sampling-based filter, like the bootstrap particle filter, or the hybrid particle filter, or the feedback particle filter. Right. Or some other sampling-based filter, like the ensemble Kalman filter, or the neural particle filter. And here I put in red the different type of filter that I will discuss during the presentation. Right. Can you still hear me? I think it would be so. This is.
Yep. Yes.
Okay. Good. So this is for the. So I'm done for the theory part, let's say, and now I want to illustrate, let's say, in 3 different settings, how this nonlinear filtering can be used and what kind of prediction it makes. So don't hesitate to interrupt me. So, right. So I will review three different applications. There could be more, but I decided for 3. And one was exactly the one that mentioned Mate and about short-term plasticity. And this is what I've been working with Mate during the CBL. So I thought talking about nonlinear filtering for an alumni talk, I couldn't escape talking about it. Yes. The second application will be on long-term plasticity, and we'll view long-term plasticity as a nonlinear filter, where the task there would be to estimate the ground truth weights. right? And here for short-term plasticity is about estimating the presynaptic membrane potential, right? And here, the last application will be at, let's say, the neural network level, where the task is to extract some feature from the sensory input and show how you can implement this at the neural network level. Okay, so now I want to describe, on this short-term plasticity, how we can see it as a nonlinear filter. And this story starts with two observations. So the first observation is that actually there is short-term synaptic plasticity. So if you have two neurons that are connected to each other, let's say presynaptic neuron, which sends its information to the postsynaptic one, and you stimulate the presynaptic and record on the postsynaptic one. So an action potential, a presynaptic action potential will lead to an EPSP, or excitatory postsynaptic potential, so whose amplitude denotes the strength of the synapse. But if you repeat this several times in a row, what you will see is that the amplitude of the second pulse here is much smaller than the first one, right? So you give similar inputs, but you have different outputs, right? So which seems like a curious transmission system, right? Biophysically, this is because there's some vesicle depletion, the vesicles are released, there's the pool is smaller, and then which lead to those smaller amplitudes. Now, this short-term plasticity can be described with sets of equations, with this Markram and so-called Markram and Sotik's model, where U is the depolarization and has some leak term and some amplitude term, right? But now, importantly, so S, I take them as a Dirac delta spikes, right? The amount by which the membrane potential increase is not fixed, but depends on this resource variable. Okay, oops, sorry. Sorry. Okay. Yeah, okay, so this resource variable is not constant, but changes a function of time. Right. So by default, it goes to 1. So if it's full, and whenever there's a spike, it gets depleted by a certain amount. Okay, so how can we see this? Oh, sorry. And then there's a second fact, right? On which this theory relies. The fact that neurons are hybrid computational units. They receive analog signal in the dendrites, which are linearly or non-linearly combined into an analog somatic membrane potential. And this gets converted to spikes. So it goes from analog to digital. And then the information, so the spike, information cross the synaptic cleft, and it leads again to an analog signal. So there's really a loss of information from the analog to digital. And the question is, based on those spikes, is it possible to reconstruct the analog membrane potential? And would short-term plasticity be of any help in this case? Right, so if you're asking this kind of question, you have to write up a generative model, right? And we wrote kind of the simplest spiking generative model where the membrane potential here follows some Orshia-Lundbeck process, where that W is some Wiener process, and there's a leak, the time constant tau, right? And the observation process, so the spikes, are drawn from some Poisson distribution, where the instantaneous rate is essentially an exponential of the membrane potential. Right. So typically when beta equals 0, the spiking is independent of the membrane potential, and when it's large, it's like the deterministic limit. Right, and then so now you can compute your filter. So if you want the mean posterior given your past spiking observation, and you can compare it to this phenomenological model of short-term plasticity that I described before, which is also called the Markram-Sotis model. Right, so this is the Markram-Sotis model, this two-variable model, which I already described before. And now you can take this, your Kushner-Stratonovich equation and compute the evolution of the mean and the evolution of the variance. And essentially, this is what you find. So the posterior mean has also two components, one decay term and an observation term, where S is the spikes, gamma is some posterior firing rate, and beta my determinism parameter. So this comes from the prime, and this comes from the observation. So S is on dn over dt, right? It's the Dirac spikes. And the posterior variance, you can also compute it, and it evolves according to this equation here. So there's also a relaxation to, a relaxation to 1 here, because the stationary prior variance was 1, and minus a term which depends on beta squared. But now what is interesting is that you can relate really almost one-to-one mathematically the mean, your mean posterior and the postsynaptic depolarization, and your posterior variance, and this resource variable. And we found this very intriguing, right? So both of them have this property that when that the first spike can be large, they respond to the first spike, which is given by this beta sigma squared, right? But then when the second spike comes, because sigma has decreased, the amplitude will be small. So it really shares this property. Please.
Jean-Pascal,
Yes.
what's gamma again?
Yes, I didn't write it here, but it's the expected firing rate, right? So you have G of X.
So that's the expectation of G of X under
under your posterior, under your filtering distribution. Yes.
Okay, so that actually depends on mu in turn, right?
Exactly. Exactly. It depends actually on mu and sigma.
Brad, does it depend on? Yeah, mu. Okay, so it does depend on S, is what I was going to ask. It does depend on the outcome. Yeah.
Actually, so sorry. I should have put it here. But so gamma is G naught times exponential of beta mu plus 1/2 beta squared sigma squared. So it doesn't depend on S as such directly, right? So here, this is, you're right, Yasha, to point it out. Here, there's explicitly an S, and here the S is not present as such, right? But indirectly, it still depends. Because when there's a spike, mu increases, and therefore gamma increases. So you have an increase in gamma, which make the sigma decreases.
It's like conditionally independent on the spikes.
Yeah, somehow you can.
Overall dependent.
Right. Okay, so then you can test. Yes, I think it's also fair to mention here, that here there are two different time constants: tau, the membrane time constant, and here the depression time constant. Versus here, we had only one time constant in the game, kind of the time constant of the OU. And here, sigma is like half of the time constant is here is half of this one. So, this raises a lot of question. I'm happy to discuss afterwards. But I just wanted to mention this on the way. So if this is your membrane potential and you have your spikes, which are displayed as vertical lines, right? Your optimal filter would take this form. Where the solid line is the mean posterior and the shaded like plus minus your standard deviation. And now if you fit your Markram-Sotis model in order to perform the same task, so to minimize your mean squared error with respect to your ground truth membrane potential, you would get this. It's literally on top of each other, which is not so much of a surprise because analytically they're really tightly related. So those two sets of equations are really tightly related. So now you can take experimental data, let's say where you look at the amplitude of the nth EPSP over the first EPSP at a given stimulation rate. And typically when the stimulation rate is small, then the ratio goes to 1 because there's no depression. And when the stimulation rate increases, there's more and more depression. And so the points are from data, and the line is here from this short-term, what I would call short-term synaptic phase. Right. But now you may wonder, well, okay, this model can only predict short-term depression and not short-term facilitation, right? Because you can only gain information, and when you gain information, it reduces your sigma, which multiplies your jump term, and therefore you can only reduce your uncertainty. But now we proposed a slightly kind of a more elaborate model, like a generative model, where you have instead of having a simple Einstein-Beck, you have a jumping Einstein-Beck, so where the mean jumps stochastically from one state to the next. And with this little addition, you have a kind of a richer filter, which can also elicit short-term facilitation, where the second EPSP is larger than the first EPSP. And this is what we obtain. Okay, so essentially, here in this first part, I argued that you can revisit the result of short-term plasticity and see them from the lenses of nonlinear filtering, where essentially the ambiguity here comes from the fact that the conversions from analog to digital is noisy, and then that you want to reconstruct it. Now, are there any questions on this part? Otherwise, I will go on this second application and show how long-term plasticity can also be seen from this nonlinear filtering perspective. Okay, so the question, at the end of the day, what is learning, right? So you can see it from a deterministic perspective, where learning is essentially an optimization. There's some ground truth weights fixed that are somewhere, and your goal when you do learning is to get there, to approach those ground truth weights. You cannot, if you cannot know your ground truth weights, maybe you can infer them, and so based on all your observation, let's say your x and y's, you can compute your posterior distribution over the weights. So this would be reframing learning as an inference problem, right? It also might be that your ground truth weights are not fixed, but change as a function of time, right? And your goal is to continuously track your weights. So with this dynamical aspect, but if you combine the dynamic and the stochastic aspect, you end up as learning as filtering, right? Where at any moment in time, you want to estimate what is your belief about your weights, right? And this is what I want to show now in the context of spiking neurons. So when neurons are spiking. So this is the problem. Essentially, we assume here that we know that we have access to the presynaptic spikes. And at the end, we will have access to the filtered spikes. So x epsilon is like the convolution of x with the epsilon. Yeah, I should have written the other way around. But okay, and the postsynaptic spike y. Right. And so here, the key assumption is to make that we're making is that the relationship from x to y is not a fixed relation. Things can change. Your environment can change, right? And so the mapping from x to y depend on some parameter that are changing as a function of time. So we'll be assuming some prior dynamics on W. Right, so what is the problem now? The problem will be to compute the posterior distribution of W given the past presynaptic spike and given the past postsynaptic spikes.
Jean-Pascal, sorry,
please,
I always have like the trouble kind of wrapping my head around this way of thinking with the, I mean, are you here describing kind of a problem that is a problem for a neuroscientist who's interested in inferring the weight of a synapse, or is that a problem that the brain is trying to solve? Because I always...
Yes, okay. That's a very, thanks, Guillaume. That's a very good question. Actually, it could be for both. I will attack it from the brain perspective.
Okay, and so this is the interpretation that always puzzled me a bit.
Yes. Okay. Okay. I think this interpretation can go a decent way, but I also agree with you. There's some part which that could also be questionable. But here the idea would be I sit in the middle of a synapse, so I am a synapse, and I can only access the presynaptic spike and the postsynaptic spikes, and this is my world, kind of.
Okay. Yeah.
Right. And the question is, how should I adapt my weights? Right.
But if the data that you have access to is the data that you take part in generating, it's like in a way you've already got the maximum likelihood solution, right? It's just you, right?
No. Okay. So I'm assuming, yeah, but that's good. I'm assuming I have taken the idealized setting, right, where I'm in a supervised learning mode. So I'm assuming
okay, I see.
My presynaptic neuron are clamped, given, postsynaptic neuron are clamped and given. And it's like it is infinitely strong teacher. It's an abstraction.
Yeah,
At this level, it's an abstraction. Mm-hmm. Actually, this is exactly the difference, if you want, between the paper of Lawrence, that we had with Lawrence and Peter in the Nature Neuroscience, where you try to abstract away from this hard teacher, and the one that I have with Yannis and also Simone, where we say, okay, let's take this idealized situation where spikes are given, right? And,
okay, that makes complete sense with the supervised setting. Yeah.
Okay. But it's an idealization, but it makes all the math and the analytics much simpler. But you're absolutely right. We have to keep aware that this is there's an idealization step. Yeah. Okay. So here we're assuming a generative model for the weights. So they follow an Orstein-Beck process and spikes. Here my dn, so n is my counting process, and dn can be either 0 or 1 essentially. And is drawn from a Poisson distribution where, like before, it's an exponential of, let's say, the membrane potential, right? And beta again is my determinism parameter. When beta is 0, it's fully stochastic. Right. So this is my function g, and my problem is to compute what is my distribution of a w given my past spiking input and my past spiking output. Right. So, this would be the only place where I just show how we can use this Kushner-Satanovich equation. So this is the Kushner equation, and here, if you take phi of w to be w, right? From this equation, you can compute what is the evolution of w, so dw. And here, well, you can well, if phi is the identity, the derivative is 1. So you just have w, you take expectation, it gives you mu. And you can just compute this term, right? And this is what it will give you. Yes, and you can do the same for the second order, right? So for phi, you have WW transpose, and you use a bit of Ito lemma. So I'm not going into the details here. But just to say that you can use this Kushner-Satanovich equation to derive the filter. Right, and here I have, so finally, so here I have the expression of gamma, which is, mathematically it's very similar to the first problem I had, but now the interpretation is very different, right? So now I'm trying to infer what is the ground truth weight versus before I was trying to infer what is the membrane, presynaptic membrane potential. Right. So now let's take this as a learning rule, right? So this learning rule has some aspect of a Hebbian learning rule, right? Where you have the presynaptic spike, right? And here the post, so you have some pre times post, right? But instead of having a learning rate, eta, right, which would be a scalar, you have a covariance matrix here, sigma, right? And this is really the big difference. This is also why it's actually not really a Hebbian learning rule, because it will introduce some cross terms, right? Because you multiply by a potentially non-diagonal matrix, right? And you also have some weight decay, which attracted the weights back to 0, right? And your covariance matrix has also its own evolution, and the stronger the input, the more it will make the posterior covariance matrix collapse within one direction. And at the end, if this is constant, this will be an eigenvalue of sigma. Okay, so maybe just a little note, right? Because actually it was a question of Mate during one of the last group meeting, you know, actually here, you can have different version of this filter. So this is what I would call the long-term synaptic filter, right? But if I allow my function f of x to be x, so I have my full sigma x transpose, right? Then I have my full synaptic filter. But this is like a n by n covariance matrix. Now I can also restrict myself to take only the diagonal elements of this one, and this is what I would call the diagonal synaptic filter. And here I want to mention that this is not just a hack on the way, right? Just for fun to remove some complexity, but you can rigorously show that this is a projection filter on the space of a Gaussian distribution with diagonal covariance matrices. So there's a rigorous way of, let's say, arriving here. And actually, you can also do it for block diagonal matrices, right? So you have to compute. Please.
Sorry, there I assume you must have also assumed in that case that, or for it to just to make sense, you had to assume that the process noise in the weights is also diagonal, and so sigma u is diagonal. Otherwise,
yes,
the first term is going to contribute of diagonal elements, and so the second term being diagonal is not of much use.
Thank you, Mate. This is a very good point. Yes, I'm assuming this is kind of my least informative assumptions somehow to assume that all my processes are independent at the first stage. So yes, I'm assuming sigma u to be diagonal. That's a very good point. But here I just want to make the fact, because we had some comment on the biological plausibility of our learning rule. So this was kind of a strong comment by the reviewers, and it's true. If you have n synapses and then you have to carry a n by n covariance matrix, can be super large, right? And you may not want to keep only the diagonal, because you have some interesting phenomena that I will show you when you have those off-diagonal elements. But you don't want to, to keep all of them. But if you restrict yourself to block diagonal, then the scaling is nice, and yet you can still keep this interesting kind of non-local interactions. Right. So now we try to compute the mean square error. So how does it perform? Right. So which is can be computed like this, where W is your ground truth weights and mu is your posterior mean, if you want, or your filtering mean. And we compared it to some gradient rule, right? And your mean squared error here is much better than the one that you obtain with the gradient rule, where your gradient rule is essentially the same, except that it has a constant learning rate here and no prior term here, right? And so we run across all the different etas, and even with the best eta, you're not as good as the one with the from the synaptic filter. Right, and so in red you have this long-term synaptic filter, and here is just like different conditions. But for all of them, for the solid line is better, for the dashed line, for the dotted line is also better. Right, so the synaptic filter outperforms the gradient rules. So even the position of the best learning rate. Another way to look also the performance of this gradient rule is to look at how things go when the dimensionality increases. Because you may wonder, say, oh, but if the number of dimension is large, maybe you have some central limit theorem issues, kind of, that everything is, the contribution of one input gets washed away by all the other ones. And that, you may wonder whether this filtering is still important. And actually it seems that indeed, so it provides some benefit compared to the gradient rule. So in gray, you have the gradient rule, so higher is worse, right? So you have a high error. And here I'm comparing the 3 different versions, the diagonal, the block, and the full synaptic filter. And as you can see, the long-term synaptic filter remains relevant even in high dimensions, right? And also that the mean squared error for the full is better than the block, which is better from the diagonal. So there's here the difference is small, but for other parameter sets, this difference can be larger. But it always goes in this direction.
Jean-Pascal?
Please. Yes, Martin?
Jean-Pascal?
Yes, I hear you.
I'm not sure. Yeah, I'm not sure. Yeah, I'm not sure if it matters in the end, but I was wondering why you chose as your kind of quality measure mean squared error in weight space rather than mean square error in output space. Because I guess in the setting that you're looking at, ultimately what you're interested in is how well you can predict, the output.
Yes. Yes.
And so I'm wondering whether you looked at that, and if so, whether you essentially get the same results, which I would expect. But
yes. So actually, yes. Actually, we have also another plot where we look at the posterior predictive distribution, where you really integrate your work. And there, indeed, the synaptic filter is also better than the gradient one. Yes. But I don't have the plot right now, just for the...
That's okay, thanks.
Yeah, but that's a good point. Thanks, Martin. Right, and so now you can also analyze this rule, right? Having worked with Wolfram on spike-time independent plasticity, I couldn't resist of also analyzing a bit what would happen if you have a different timing between the pre and the post-synaptic spike. So if you have a pre and then a post, this leads to potentiation, right? And if the timing is reversed, you have depression, where the potentiation time window here, it's really given by the EPSP time constant, right? And the negative window, like the time constant of the negative window, is given by the bias. So it's true, I didn't introduce the bias so far, but I'm assuming that the membrane potential is the weighted sum of input plus some bias, which also has some Orstein-Beck process, which follows also some Orstein-Beck process. So as if like the x0, the first input was just a constant. Right. Okay, and this nicely matches like experimental results that many of us know, that if a presynaptic spike is before a postsynaptic spike, you have potentiation. If the timing is reversed, you have depression. So in this sense, the synaptic filter is consistent with spike time independent plasticity. It also goes beyond. It makes prediction that the variance, that the EPSP variance should change as a function of the timing difference between the pre and the postsynaptic spike. But here we didn't have data or conclusive data to make a comparison. Right. So it's some kind of a second order STDP, if you want. Yes. And now comes the interesting thing about heterosynaptic plasticity. So one consequence of this synaptic filter, this long-term synaptic filter, is that you have heterosynaptic plasticity. So if you have two synapses that are stimulated by, let's say, the same protocol and target a postsynaptic neuron, they receive, say, correlated input for a while, right? So we say they have a precondition. Now, if you have a presynaptic spike, but and then a postsynaptic one, this connection from the first neuron to the second one will be potentiated. So this is, we call it homosynaptic potentiation, right? But this connection here that hasn't received any input actually will be depressed, right? So and this the depression that comes here precisely comes from this preconditioning matrix, the sigma that multiplies this pre-post term in the learning group, right? So if a presynaptic spike is before, you have potentiation. When the timing is reversed, you have depression. But here, if you consider the but there's no heterosynaptic plasticity. So in red here, nothing will change for this connection if you consider the diagonal synaptic filter, right? So the diagonal synaptic filter exhibits homosynaptic STDP, but no heterosynaptic plasticity, right? Because there cannot be crosstalk between synapses, precisely because you multiply your pre-post term by a scalar instead of multiplying by a matrix, right? But here, if you consider the full synaptic filter and not the diagonal synaptic filter, right? So when you have potentiation here, like pre-post leads to homosynaptic potentiation, but the other synapse, like this synapse, will show depression. So you have heterosynaptic depression. So this full synaptic filter elicits homo and heterosynaptic plasticity after some preconditioning, right? And the nice and the interesting thing here is that those two are anti-correlated, right? So if there's potentiation for one, there's depression on the other one, right? So this is how we our simulation results. If you have homosynaptic potentiation, you have heterosynaptic depression. So if you have LTP on one, you have LTD on the other one, and vice versa. So there's some anti-correlation. And actually there's some experimental support for this as well. It's connection from BLA to ITC. There's also some anti-correlation between homosynaptic plasticity and heterosynaptic plasticity. Right, so there seem to be some, so some nice argument for this synaptic filter. And maybe you don't want to have the full synaptic filter, because of scaling, but maybe a block diagonal version where dendrites compute locally. The effect of those blocks might be, let's say, a way forward. Okay, so this was for the two first parts. Now, how do I do with time? I'm more than happy to cover the third part.
I think we are near the end of the hour. So
okay.
What I would suggest is that if you can summarize it in a couple of minutes, and then if people have questions at the end about it, then obviously that would be a good opportunity to kind of tell us more about it.
Okay, so you give me 5 minutes or 2? It means, or 2 minutes?
Absolutely. five. You can
okay.
have five.
I would say that if it involves Mbappe again, you can skip.
Was not meant to be an offense for all the French people attending. Yes. Okay. But you, Guillaume, you're more than welcome to come at our place and see the, the Swiss team playing actually right now. Okay. So far it was. So we had a parametric representation of the distribution, but you can also have particle-based, right? And okay, let me see if I can do this, right? And I'm sure you have learned about the bootstrap particle filter. Okay, this here, right, where the distribution is represented with particles and weights, right? And the term here directly comes from the Kushner equation, right? But this really has some serious trouble in terms of dimensionality. If you go in high dimension, you have some massive problem. All the weights collapse to 1. And there's some nice argument we made, like in SEM review, why you do have this. And you have a scaling 1 over dimensionality. In terms of biological implementation, it's really unclear how the brain could implement such a bootstrap particle filter. Now, on the other end of the spectrum, you can have feedback particle filter where all the weights are 1 over n instead of being weights. So you escape this problem of a weight collapse. Okay, I'm not going to the details of this feedback, but then you have to pay a price, and the price you're going to pay is to estimate your gain matrix here, which multiply your innovation process here. So it doesn't seem to be the full solution there, right? You also have the hybrid particle filter. This is something we did with Essan, like to generalize all the existing particle filters, including bootstrap and feedback particle filter. And we also went for the neural particle filter, which is maybe a biologically plausible version of this filter. So so all the distribution is represented with particles. Yes. Okay. Maybe here just one word is that with this unweighted particle filter, with this neural particle filter or the feedback particle filter, you have you require only a linear number of particles as a function of dimensionality, where the bootstrap, sorry, this should be B, the bootstrap particle filter, you literally have an explosion of the number of particles you require in order to do the computation. So here, really, this sounds like a big promise for particle-based filters. Right, and okay, so this probably likes it because it's consistent with this sampling hypothesis, right? It also has this flavor of, when there's a stimulus on set, the variability decreases, right? With a little twist is that this quenching of variability happens at 1 time scale, but we predict that there should be another time scale for the recovery after the stimulus offset. This could be nicely checked as well. So maybe I skip this one. You can also do learning. Yes, and then arriving at the end of my 5 minutes. But here, yes. So really, just to take one step back. So the goal here was to say, okay, nonlinear filtering, I think is really a super cool technique that can be applied at a different level, either from the computation side, like at synaptic level, network level, behavior level, or as a data analysis tool. And I think I learned a lot by applying this technique, and I think yes, it's a cool technique. Okay. Thanks for your attention, and I'm more than happy to take any question here.
All right. Yes, anybody has a question?
Hi, Jean-Pascal.
Hi.
Thanks for the talk. It's great. I really like the way you present it. It's pretty clear. So I have a few questions about,
Yes.
firstly, the short-term plasticity part.
Mm-hmm.
So there you have a slide comparing the touchscreen macro model and your short-term synaptic filter model, right? There,
Yes.
I think, yeah. In the illustration there, you have compared, yeah, just lost the slide.
Yes, this one?
The previous, no, the 16, number 16, yeah.
Okay.
So, yeah. So on the left-hand side, we have seen that the EPSP ramping up first and then go down, right?
Mm-hmm.
So
yes.
But in your synaptic filter, I see it's basically ramping up. I don't see the train of going down. I'm wondering if that could be fixed by tuning your parameter, or just it's going to be a long-term trend, or does it have anything to do with the time constant you have been using here? Okay,
so I mean, here, as I briefly alluded to, there are two different time constants, right? So there's, let's say, a membrane time constant, tau, which tells you how fast this membrane potential goes down. So one, you have an increase. Let's say this would be this time constant here. But there's a second time constant, which is the depression time constant. It says how fast those amplitudes, or how much time will it take for recovery of those small amplitudes. So if I wait some time and have a new EPSP, how much time do I need to have a full recovery of my EPSP? So technically here I have two time constants versus here I have only one in the game. So you can argue that this is a form of a very short-term plasticity, as it is called, right? Okay. There are different ways of addressing here, right?
Yeah. So I'm just wondering, in the dynamic of the posterior variance, where if by comparison I'm just comparing the tau over 2 to the tau d in the the one. So I'm wondering whether why you're using tau over 2 instead of maybe other parameters, or that's just the result of the...
Exactly, this I cannot tune. This is just the result of my filtering problem, right? And essentially in my filtering problem, I inject only one time constant, which is the Oxtenberg time constant. And, out I can have only one filter which has only one time constant. This is, yes.
Okay.
Yes.
So in terms of the interpretation of this time constant, this tau over 2 here, because I'm treating in the previous model, the tau d could be interpreted as the how quickly the resource is distributed, and but in this short-term synaptic filtering model, this tau over 2 seems to be related to how quickly the posterior variance is approximated.
Yes. So let's say the tau here is really the time constant of the presynaptic membrane potential, right? So it doesn't, I have to say, it doesn't need to be a membrane time constant, right? It can be actually much longer, right? If this neuron receives some stimuli that slowly oscillate, let's say, so if the stimulus has a time constant on the order of hundreds of milliseconds, so this tau would go on the order of hundreds of milliseconds as well. Let's say, right?
Okay.
Yes.
Okay,
now it's also possible to include other time constants in the game, right? So there could be some refractoriness here, right, included, which I didn't. But essentially here in my generative model, in this generative model, there's only one time constant, and out there can be only one. Out in the future. Yes.
Okay. thanks. And I have another question for the long term.
Yes.
Yeah. So can you go to the slide that you shows? Let's see. So the one that it shows the STDP model. Oh yeah, here. Maybe it's just a clarification question because maybe you have mentioned it. I'm wondering where in this model did you incorporate the time delay between the pre and post part? Because I've seen here XT is a pre and NT is a post part, right?
Yes. So here I'm in a supervised learning context. So my XT is a spike train, right? So yeah, X has some spikes, presynaptic spikes, and X epsilon is X convolved with an EPSP curve, right? And my dn of t is my postsynaptic spike. So if X epsilon typically lasts, say, 20 milliseconds, and if it's still high, then it multiplies by 1 here, then my dn would be 1 if there's a spike. Just let's say 10 milliseconds afterwards, my PSP is still large, and you read off this large value, right? So this is where you will set up the timing. So it's a supervised learning context. So if you enforce when is X and when is Y or dn.
I see. Okay. Okay. Thanks. And just a final question about the result of heterosynaptic computation. So in that part, I've shown that without the diagonal synaptic filtering, you don't see the computation at all. So that means in order to show this good result of synaptic plasticity, you have to actually consider the non-local information in the dynamics of the covariance.
That's absolutely correct. Yes.
So in that case, it's possible that this synapse does not have the access, or there's actually no synapse between the pair of neurons that you consider the covariance about.
Yeah. So okay. Yes. So here we're making the assumption that there's some modules, and those modules here in the model would represent the set of inputs that belong to the same block. Let's say if you have 5 synapses that belong to the same block, so this would be a module. And on the biological implementation, you could say, well, maybe some synapses could target the same dendrites, and we know that actually nearby synapses on one specific piece of dendrite are correlated versus synapses between two different dendrites are less or not correlated.
Okay.
Yes.
Great. Thanks for your explanation. Thank you.
Okay, thanks for your questions.